Hello, everybody. Today starts Unit 5, specifically our first section, 5.1, which is all about exponential growth and comparing to linear growth. And to start off class today, we actually had an awesome vote. It was posed in a video that I showed at the start of class, so I am going to actually play that video right now so that you have the ability to have the same experience that those in class did. In class, I had everybody who voted for option 1 penny to go to the left side of the room, anybody who wanted the 3 million to go to the right side of the room, and what I just said will make sense when I play the video. So I'm going to play that right now.
I'm Lynn Moore from TheMillions.com, and I like to paint a scenario for you. Let's just say one sunny day on one of the dozens of Peachtree streets in Atlanta, you just happen to run into billionaire Arthur Blank at Chipotle. You guys strike up a convo in line. He thinks you a cool, crazy person and decides to give you an opportunity of a lifetime. He tells you, pick one option. He would take $3 million right now for 1 penny that will double in value every day for 30 days. You look at Arthur Blank and say, "Boy, awesome. You crazy." Arthur Blank gives you that look, like he's dead ass serious. So you start to wig out because you're like, this is for real. Within moments, you could be a millionaire. But you keep thinking to yourself, $3 million. But on the other hand, why would he offer me a penny? Is there something special about this penny that he knows that I don't? Which option would you choose? Well, let's take a look. If we decide to go with option A, Mr. Blank is going to write a fat check for $3 million, and you're done. About an hour from now, you're going to be on that first flight to Turks and Caicos. In the story. Now, option B is a little bit more involved because all you're getting is one ugly, discolored penny that will double in value every day for 30 days. So by day 2, you got like 2 cents. Well, at least you could buy a 6-pack of nothing. But no worries, hombre. You still got 29 days to go. And by the end of the first 7 days, you will have a whopping balance of 72 cents. Oh, hell. You think to yourself, I'm messed up now. 72 cents when I could have $3 million. But you know what? Just fast forward to day 14 of your account. Your balance is now $92.16. Oh, snap. Oh, snap. Out of control now. I'm out of control of the Waffle House at Lindbergh Station. And you know what I'm going to do? You know what, everybody? You know what? Lemonade's on me. Lemonade's on me. Now, look here. 3 days later, your money has grown to $737.28. Pow! And then on the 21st day, you're still sitting on a cool 11 grand. That's more money that you paid for than your Buick that you're driving like right now on them 10-inch rims. But they clean, though. By the time you make it to the 28th day, you only have $1.5 million. Even though $1.5 million isn't chump change, but it's not $3 million either. Now listen up, a word of advice. Don't go tell your wife that you chose one dirty old penny over $3 million. Hold on. The very next day, your account shot up to a gargantuan amount of $3,019,898.88. You still have one more day to go. Just 4 weeks ago, you thought you had made the biggest mistake of your life by choosing a janky old penny over $3 million. But now when you walk in the bank, they know your name is Mr. $6,039,797.76. Man, I like that bank. Most of us as adults have never been taught anything about
Brandon calling 6 report to the main lobby. Brandon calling 6 report to the main lobby.
When we found out about compound interest, it was working against us and not for us in the form of monthly credit card finance charges. Look, quit hating on yourself. Become educated on how money works today. With websites like FDIC.org, Fidelity.com, there's a million of them out there. Also, too, make sure you teach your kids to do the same. They got to learn about money. Visit websites, for example, like PlanetOrange.com, Rich Kids, Smart Kids. SmartKid.com, or better yet, give them a quick course in reality and show them all the bills you pay every month. By the time both of you guys finish doing that, I guarantee there won't be a dry eye in the room. Either way, it is not okay to continue to be deaf, dumb, and blind when it comes to dealing with your finances. Thanks for watching. Peace.
So that rounded out the intro video we had at the start of class, and it was an awesome way to introduce this topic that we'll be talking about, which is exponential growth. Now, the video talks specifically about compound interest, which deals with exponential growth, but that's an application that we'll be talking about more towards the end of the unit. Today's notes is the building blocks, so to speak, about what this type of growth really looks like. And many of us did do some work with tables last year, and so I'm hoping that these notes are a little bit of prior knowledge, hopefully not brand new, but we'll see as we go through our examples. So jumping right into number one, it says, how are linear and exponential functions different? Let's look at some input-output tables. So the first thing I would like you to look at are your x values. Specifically, how are the x values moving? How do I get from -2 to -1? How do I get from -1 to 0, 0 to 1, and so on? Just give this box a second to get out of the way. So to get from -2 to -1, I add 1. Add 1 to this, I get to 0. 0 plus 1 is 1. 1 plus 1 is 2. So we can start off our sentence by saying, as x increases by adding 1. Now we want to look at the y values. When I look at my y values, to get from -4 to -1, I would add 3. Now I can ask myself, what is -1 plus 3? -1 plus 3 is 2. 2 plus 3 is 5. 5 plus 3 is 8. So we'll finish this statement by saying, as x increases by 1, adding 1, y increases by adding 3. Because this is moving by addition, I know that this is a linear growth. Number 2, when I check 5, 6, 7, 8, 9, x values are still moving by 1, adding 1 each time. Now when I look at my y values, I'm looking for a pattern. To get from 4 to 8, 4 plus 4 is 8, but 8 plus 4 is 12, not 16. I need to get to 16. So now I ask myself, well, 4 to get to 8. Well, 4 times 2 is 8. 8 times 2 is 16. And if I keep multiplying by 2, it works. 16 times 2 is 32. 32 times 2 is 64. So here, as x increases by 1, because my x values are still increasing by adding 1, y doubles. Or you could say increases by multiplying by 2. And because this table moves by multiplication, it is exponential. Number 3, -3, -2, -1, 0, 1. X is still moving by 1, so as x increases by adding 1, let's see what happens to our y values. I notice 64, 16, 4, 1, and 1/4. When we see whole numbers, and as it grows, it's actually becoming smaller and becomes a fraction, division should be on our minds. Maybe I'm not sure about 64 and 16, but I do know that 16 divided by 4 is 4, and 4 divided by 4 is 1, and 1 divided by 4 is 1/4. Think of if you have $1 and I asked you to divide $1 by 4, you would tell me 25 cents. That's what 1/4 represents. So really, if you're not sure, the only thing you'd have to check is 64 divisible by 4, and do I get 16? And you do. So this table is moving by division. But we're going to formalize notes on this in a second. I'm going to say right now that we need to remember dividing by 4 is the same as multiplying by 1/4. And when I finish my statement, I'm going to specifically say that y decreases by multiplying, multiplying by 1/4, which means that this is also an exponential table. Number 4, -1, 0, 1, 2, 3, x is moving by 1. As x increases by adding 1. Now let's look at the y values. To get from 9 to 8 to 7 to 6 to 5, well, 9 minus 2 is 8. Excuse me, not minus 2. Minus 1 is 8. 8 minus 1 is 7. 7 minus 1 is 6. And 6 minus 1 is 5. So y decreases by subtracting 1. Because this is moving by subtraction, I know it's linear. So now that we've looked at a couple of examples, let's really formalize the difference between linear functions and exponential functions based on the operations taking place in the tables we just worked on. Linear functions increase or decrease at a constant rate. That constant rate is known as the slope. It's also called rate of change. And hopefully as I write this, this is a blast from the past from Algebra 1 last year. Slope or rate of change, both mean the same thing, are directly connected to adding and subtracting. Now, exponential functions are much different. Exponential functions increase or decrease by a multiplicative. So like multiplication is the start of the word. Multiplicative. So and then instead of multiplication, write A-T-I-V-E. Multiplicative factor. That value is known as the growth factor. And is directly connected to multiplying and dividing. But notice, it's a multiplicative factor. So if, for example, in our table, when division took place, we still needed to write that in terms of what you are multiplying by. And we'll practice that again. Before we move on, let's go identify the slopes and growth factors. So in number 1, Number 1, it's linear because it's moving by addition, so that means I will have a slope. My y values, I'm adding 3 each time. So my slope is 3. And I will highlight that so it stands out. Something that I would like to remind you of from last year, when you were working on slope last year, slope is always change in y divided by the change in x. Here, my change in y is my 3, and change in x is 1. In fact, in all of these examples, they were built so that the change in x, which will be in the denominator always here, is 1. So that's why for these examples at least, we can just identify the change in y and we're done. Because again, the x values in all of the tables are adding 1. Dividing by 1 doesn't change the value. Number 2 is exponential because it's moving by multiplication, which means I do not have a slope, I have a growth factor. Here the growth factor is 2 because we are multiplying by 2 each time. Highlight that so it stands out. Number 3 is also exponential. So ask yourself, do you have a slope or do you have a growth factor? I'm hoping we're all saying growth factor. Remember, this is a multiplicative factor, so it has to be in terms of what you multiply by. So yes, I see that I'm dividing by 4. That's my first thought. But we know that dividing by 4 is the same as multiplying by 1/4. So when it comes time to state the growth factor, we state it as 1/4 because that is what we multiply by. Lastly, here with number 4, it's linear. Do you have a slope or do you have a growth factor? We have a slope. Here the slope is -1. Numbers 5 through 8 is a great opportunity for us to apply this knowledge. So I'm going to actually work on number 5, and then I would like you to work on 6, 7, and 8. The directions say each of the tables below represents a function. For each table, determine if the data shows an exponential function, linear function, or neither. If it's linear or exponential, state the initial value and the rate of change or growth factor. So when I look at number 5, 0, 1, 2, 3, 4, x is moving by 1, 3, 15, 75, and on. This definitely looks like it's growing very quickly. So my first thought is to see if multiplication might work. So to get from 3 to 15, that's multiplying by 5. And then I will either use my mental math skills or try on the side or use a calculator. What is 15 times 5? You need to pause this to go grab your calculator. Go get it. When we do 15 times 5, we do get 75. And then check, is 75 times 5 375? It is. And then last but not least, check, is 375 times 5 1875? And that should come out to be a yes. So because this is moving by multiplication, specifically multiplying by 5, I'm going to say that this is exponential. Let's take some notes real quick on initial value. Way back when, if I asked you, I wrote this and I said, what's my initial value? I'm hoping we'll all say that B is the initial value, because that's my y-intercept. And some of you might be saying, oh yeah, I know that. I know you know that. So for y equals mx plus b, B is the initial value. But here, I have tables. I don't have an equation. So we're going to write ourselves a little note. When x equals 0, what's y? So if I look in my table for number 5, I do see x equals 0, here's 0, and then there is y is 3. So that tells me my initial value is 3. Another way to look at this, if you were to actually graph this ordered pair 0, 3, zero in the x position of the ordered pair means don't go left or right, just go up to 3. There's your y-intercept. So that is why we're going to look when x is 0, what's y? That will be my initial value. And there's our connection to graphing. Because this is moving by multiplication, I know that I have a growth factor. You have to commit to which one of these you have. If you don't circle one of these, it's going to cost you some points because you're not telling me that you understand the vocab. So if it's moving by multiplication, it has a growth factor. Here the growth factor is 5 because that is what we're multiplying by. This process is exactly what we're going to do for 6, 7, and 8. So press pause real quick and try 6, and then I will join you. For number 6, I see 15, 13, 11. The first thought that comes to my mind is to try seeing if subtracting 2 works, because 15 minus 2 is 13, minus 2 is 11, minus 2 is 9, minus 2 is 7. That worked. So this is moving by subtraction, so I know that this is linear. For my initial value, I say when x is 0, what's y? So I look. There we go. Here, when x is 0, y is 9. So my initial value is 9. And I know that because this is linear, I have a rate of change. That rate of change is -2 because that's what we're subtracting by. Number 7 is kind of a really cool example because let's think about this. I see that my first y value is 0. Now, I can't multiply 0 by anything to get 1. So now my only option is addition or subtraction. Well, to get from 0 to 1, I add 1. To get from 1 to 5, I add 4. Right there, I know that this is neither. And here's my proof. This is all I would need you to write for me to understand that you know why this is neither. If I see a blank table, I might think you just did like eeny, meeny, miny, mo. So make sure you give me some kind of explanation or sentence or notation here to tell me you understand why it's not linear or exponential. Number 8, go ahead and try by yourself, and then I will join you on it. For number 8, to get from 243 to 81, I divide by 3. 81 divided by 3 is 27. 27 divided by 3 is definitely 9, and 9 divided by 3 is 3. So because this is moving by division, I know that this is exponential. I look to see when x is 0 right here. Initial value is 3. If it's exponential, it has a growth factor. And remember, though, I'm going to write this, and I'm going to put a giant X through it. We are not going to write that there. We need to say, what does this mean in terms of multiplication? Dividing by 3 is the same as multiplying by 1/3. The growth factor always has to be in terms of multiplication. Let's talk about what the equations will look like. Highlight these to help them stand out. Linear functions from last year, I'm hoping everybody thinks of y equals mx plus b. That's our go-to standard form, or excuse me, it's not standard form, it's slope-intercept form, but it's the first one that usually comes to our mind, where m represents our slope or rate of change. They mean the same thing. And b represents the y-intercept or initial value. We also have point slope form, which is y minus y1 equals m times x minus x1. And in class today, we kind of played around with the notation. And what I mean by that is that I actually posed this challenge. I said, well, is there anything that prevents me from writing y minus k equals a times x minus h? Where instead of using x1, y1, I chose to write the point as h comma k. And instead of writing slope using m, I said a slope a. And we talked about how the answer is no, because a variable is just that. It's a variable. We can choose any letter we want. I did have a reason for doing this, which will be clear in about a minute, but the only thing I'm going to ask you to do right now is ask you, if I were to solve this for y, how would I do that? Well, I see that it says y minus k so I'm going to add k to get y by itself. So I get y equals a times x minus h plus k. Before we talk about the exponential models, I want us to extend our thinking of what b actually does to the graph. Yes, b is the y-intercept. Yes, it's the initial value. But it is also a shift. It's a shift up or down. In class, we talked about some examples, like if I had a b value of positive 3, that means that the entire line is shifted up so that the graph will cross the y-axis at positive 3. Or if I had a b value of negative 10, that means the entire graph was shifted down 10. The line is now going through negative 10. So that's a vertical shift down. This plus k also represents that shift up or down. I'm going to let that be for a second. I'm going to draw a line all the way across to separate the notes for linear versus exponential. And we're going to put this concept on the back burner just for a second. Exponential functions, the model looks like this. Y equals a times b to the x, where a is my initial value and b is the growth factor. Another way of writing this exact same exponential model, but this time accounting for possible shifts, it's going to look like this. Y equals a times b to the x minus h plus k, where k represents a vertical shift up or down. And this is where in class we talked about this connection. Here I was able to rewrite this model, my point slope form, to have a k value, which would represent an up or down shift. Here I also have plus k, which is a vertical shift up or down in my exponential model. Then in class, we kind of guessed. I said, well, if k represents a vertical shift up or down, that means that h eventually will be a horizontal shift left or right. People kind of guessed that correctly, so I wanted to mention that. This is as far as I'm going to go with the models in these notes. I just wanted to get them on the table because as of tomorrow, we're going to really start to dig more into how to actually use these models. But for today, we're just going to get them on paper. Let's talk about what the graphs will look like. A linear function is any straight line you want. So use a straight edge. Go ahead and draw a straight line. Totally your choice what it looks like as long as it's straight and it's got arrows at both ends. It comes out to be linear because we have a constant rate of change. What we mean by that is that if, for example, this is up 1, right 2, so positive 1/2 slope, if the slope is 1/2 here, it's 1/2 here, it's going to be 1/2 here, it's going to be 1/2 no matter how far you go on this line. The slope is constant. The rate of change is constant. Exponential functions look nothing like this. Exponential functions kind of start off slow and then they grow very fast. So for example, from here to here, the slope is 1, but then if I try to count from here to the next point, I have to go up 1, 2, up 3, right 1. So here the slope is 1, here the slope would be 3. That is not constant. That is an exponential growth. Let's make a note. Grows fast. At the end of today's class, we had about 5 to 10 minutes in class to actually work on this small set of practice. So at the top here, I'm just going to make a note to you that 5 to 10 minutes at the end of class. Finished. This was 1-5. Yeah, I guessed it. Good. My memory serves me correctly. There was 5 practice questions here. So you're watching this at home right now. Go ahead and work on 1 through 5 on your own using your notes to help you. And tomorrow, first thing, the first minute or so of class, we will actually be checking these answers as a group. Have a great day, everybody.